Right. So, we are going to continue the lecture from last time. So last time I mostly gave some motivation for model categories, and I explained some of the parallels between chain complexes, simplicial sets, and topological spaces. Right, so in all of the cases, we wanted to deal with homotopy equivalences, which are some kind of strong equivalences. And then they are too complicated to handle, so we had to replace them by weaker equivalences, which were quasi-isomorphisms, weak equivalences, and weak equivalences. They are both called like that in the two categories. And we realized that in order to deal with all this, we had to look at some lifting properties to find some models, some objects for which the two notions were equivalent, right? So for chain complexes, these were simply surjections and injections. For topological spaces, these were Serre or U of X fibrations, and cofibrations, again, Serre or U of X cofibrations. And for simplicial sets, I didn't really talk about it, but you can also think about injections, because an injection of simplicial sets on geometric realization becomes a subcell complex, and subcomplexes are precisely well, more or less cofibrations in topological spaces. So we have this whole analogy between these three cases. And so today what I'm going to present, and I'm going to write again the definition, is the definition of model categories, which is some kind of unifying framework of the three possible homotopy theories that we are going to study, right? So like last time, I will disable my camera because you will not see anything, because my computer is going to be flat on my desk. So. All right. So I'm going to write again the definition of model categories. So beforehand, I'm going to just make a few definitions, because there were some questions about it in the Slack or the Discord. So first of all, convention, because this will matter at some point in the course. For now, we can more or less ignore this thing, but all of our categories are locally small. So for all x, y in C, from C of x, y is a set. So most of the time we can just forget about this condition, but in some cases it's important to have this, especially when we deal with localizations, or when we are going to deal with the small object argument, right? And I'm going to make a definition. I quickly talked about it last time, but I want to say it again because there was another question about it. So let's see the category. And A, X, two objects. We say that A is a retract of X if there exists a commutative diagram like this. Maybe I will call it sigma X. Here, rho, such that this is the identity of A. Right, so you can think of sigma as being some kind of section. Oops, sorry. This is a section, and here this is a retraction. So you should not confuse the two words, right? There is retraction and there is retract. And so this means, if you think about it in terms of spaces, that A is a subspace of X, and X retracts onto A, right? And moreover, if F from A to B is a morphism. And let's say F prime from A prime to A prime, X prime is a morphism, is an over. Then F is said to be a retract of F prime if there exists a commutative diagram like this. So first of all, A is a retract of A prime. Here you have F. Here you have B. And I should have called this B prime to be consistent. B is a retract of B prime. Here you have F. Here you have F prime, and this whole thing commutes. Right? So it means that the source of F is a retract of the source of F prime. The target is a retract of the target. And you can find the, well, a section and a retraction in a way that everything commutes. Okay, so this is a generalization of the notion of retractions or retracts to basically the category of arrows. All right. So is this okay for everyone? This notion? Yeah.
J'ai une question.
Oui.
Est-ce que est-ce qu'on se donne les flèches? Est-ce que la rétraction c'est l'existence ou c'est la flèche avec la flèche? Vous voyez ce que je veux dire?
So the question is a retract if arrows exist or are they part of the data? No, if the arrows exist, then we say that A is a retract of X, but there can exist many possible arrows.
Okay, thanks.
It's not, there can exist several possible sections and retractions, but in all cases, we say that the object is a retract of the other one, or that the morphism is a retract of this one, but it's not necessarily part of the data. Okay. Other questions before we start with the definition? No? Don't hesitate to interrupt me. I know it's not easy when we have online classes, but we have to deal with it. So I'm going to give again the definition of the model categories that I gave last time. So as I said, this is probably the most important definition of the whole course, and it's a bit long. So you have to work a little to understand it. We are going to see some properties of this definition soon after, and then some examples. But anyway, here is the definition. So a model category is a category C equipped with 3 classes of morphisms, W, C, and F. So W is for weak equivalences. C is for cofibrations. And F is for fibrations. And usually a weak equivalence will have this notation. I will put a little tilde on top of the arrow. The cofibration, I will put this tiny hook at the beginning. And the fibration, I will put 2 heads for the arrow. In the literature, you can sometimes find this notation for cofibration and this notation for fibrations, but well, I prefer this one, and I guess it's a little bit more common, but this one exists also. And here, to get back to the questions I had before, this is really part of the data, right? this is part of the data of a model category. A model category is really a category C and 3 classes of morphisms, right? There can be several possible model structures on a single category, right? We are going to see some examples just after. Satisfying the following axioms, right? So the axioms are typically numbered from 1 to 5, MC1, MC2, and so on. So MC1, the property that C is complete and co-complete, which means that C admits all limits and co-limits indexed by small categories. Okay. So by small categories, I mean that of the category and morphisms of the category form a set. So again, this is the kind of set theoretical issues that we are not going to talk much about, but it's important to say at some point because it's not possible for a category to, in general, to admit really all limits and co-limits. Actually, there is a theorem which says that if a category has all limits and co-limits indexed by big categories in addition to small ones, then the category has to be a poset, partially ordered set. So it's very restrictive, right? So the second condition is that W satisfies the 2 out of 3 property if F and G are composable morphisms and 2 morphisms out of F, G, and G circle F are in W, then so is the third one, right? So as I said last time, this is really 3 axioms in one, because it says 3 things. If you have a triangle like this of morphisms, and 2 of the edges are in W, then so is the third one. So first of all, it means that if you have 2 morphisms in W and their composition is in W, it means also that, for example, if you have 2 morphisms with the same target and you have a third one which makes this triangle commute, and these 2 are in W, then this one is. And also if these 2 are in W, then so is the third one, right? So this is really 3 axioms at once that you have to check essentially separately, right? Okay, so any questions so far? I mean, it's pretty... so the 5 axioms are basically ranked in order of not necessarily difficulty, but pretty much difficulty. Like this one, well, it's something you have to check about your category. It's some kind of condition. This one is usually easy to check. The second one is also easy to check in general. Well, the third one, I guess. If F is a retract of G and G is in W, respectively, C or F, then F is in W, respectively, C or F. So if you have a morphism which is a weak equivalence, then any retract is a weak equivalence. Same for cofibrations and fibrations. So this one is a little bit harder to check than this one usually, but it's not too bad. The fourth one starts to become much harder in general. So consider a square like this, commutative square, where you call this map I and this map P. Well, you have two axioms. First one, if I is in C and P is in W and F at the same time, then there exists a lift. So a lift is a map like this that makes both triangles commute. And similarly, there is a symmetrical axiom that says that if I is at the same time in C and W and P is in F, then there exists a lift, right? So in both axioms, this is why I draw the square like this. The left one is supposed to be cofibration. The right one is supposed to be a fibration. And if one of the two is a weak equivalence, then there exists a lift. All right? And finally, MC5, any morphism and meets two, so let's say a morphism F from X to Y, and meets two functorial factorizations So you can either factor it as a cofibration, which is a weak equivalence, followed by a fibration, or you can factor it as a cofibration, followed by a weak equivalence, which is also a fibration. And as I said earlier, checking this axiom is also typically very hard, perhaps even harder than checking MC4, right? Okay, so there is a question in the chat. What do you mean exactly by functoriality of a factorization MC5? It seems to be important to prove that H0 of C is equivalent to H0 of CC. Well, so let me make a historical remark. So, sorry. When Quillen introduced model categories, he didn't ask for functorial factorization. Well, for factorizations to be functorial, he just asked for them to exist, but not necessarily to be functorial. And it's possible to prove that all the following statements in my notes are still true. It's simpler. And typically, well, to my knowledge, there are not really interesting examples of model categories where you don't have functorial factorization. So nowadays, people always ask for factorizations to be functorial. So what do I mean by functorial factorizations? Well, I mean that if you have two, well, I mean several things. First of all, if you have two things, no, sorry, I don't mean that. I mean that if you have two maps like this, and you have a morphism in the error category, then you have morphisms between the factorizations. With a fixed thing, and also for CF, right? What do you mean not unique? Oh, okay, yeah, it's not that it exists, it's that like all, I mean that P is a functor, and if you think of it as alpha 1 and alpha 2, and you think of this as some kind of map in the error category of alpha, and this is P alpha, right? The functor P assigns something to this two morphism between PF and PF prime that makes the thing commute, right? It's not really that it's unique, it's more like it's part of the data. It's part of a functor, which is called P or C for this one, and which assigns to any commutative square like this, a commutative rectangle like that. All right? Okay, so any other questions about this, this definition? So let me just mention, so I already said that historically people at the beginning didn't ask for factorization to be functorial, but now they do almost all the time. Also, the axiom MC1 used to be slightly different, and Quillen actually called what I'm defining now, Quillen used to call a closed model category. But nowadays, people don't really use non-closed model categories. So this is what people call model categories now. Nobody uses the axiom, the adjective closed anymore, right? But if you read an old paper, then it's possible that you read closed model category, and this is a closed model category, right? So there is a question, does it imply that the fibrant replacement functor is well defined? Yes, but I haven't talked about fibrant replacement yet, so just have to wait 5 minutes for this. Maybe one last thing here is that here I said that the lift exists. Of course, it's not unique in general, right? Okay, so this is the definition of a model category. It seems a bit maybe intimidating at first, I guess, but as you are going to see, it's not so bad. Really, once you know you have a model category, working inside the model category is not so difficult. The most difficult part usually is to prove that you have a model category, and this is really, really hard in general. To prove that some category and some classes of morphism satisfy the axioms is not easy, often, in most cases, except maybe trivial cases. But like, for example, topological spaces, it takes quite some time. Okay, so there is a question. Someone says there is a problem with the diagram at the bottom right. Well, there is a prime missing here. Is that the problem?
Non, c'est juste que la flèche à droite, elle va de x vers x'.
Oui, F, ça va de x vers y, normalement. De toute façon, c'est F qu'on a factorisé.
Ah, pardon. Oui, bien sûr. Ça, c'est alpha 1. Ça, c'est alpha 2. Oui, ça c'est F. SSF prime. Ok? C'est tout bon? Okay. Okay, so let me give also some definition. Morphism, which is in C intersect W, is called an acyclic cofibration. And a morphism which is in F intersect W is called an acyclic fibration. So this is just a name for a cofibration or fibration which is also a weak equivalence. So as a remark, sometimes people write trivial cofibration and trivial fibration, but well, it's a matter of preference, I guess. But also trivial fibration could be confused with trivial fiber bundle, so I prefer this one. Another definition that we are going to use sometimes is the following. I said, so a morphism I said to have a left lifting property abbreviated by LLP with respect to a morphism P, and conversely, as you can guess, P has a right lifting property with respect to I if for any commutative square a lift exists. All right. This is denoted by I is orthogonal to P, which it's not really a relationship with linear algebra, it's just a notation. Or I is in LLP of P, or P is in RLP of I, right? So there is a question, are the three classes of morphisms stable by composition? And someone already answered, no, it's a consequence of the axioms. We are going to prove it in a few minutes, actually. But you don't have to assume it, actually. This is going to be a consequence of all the other axioms. Right, so let me just finish with this definition. For example, axiom MC4 tells you that C is included in LLP of F cap W, and that C is orthogonal to F cap W, or that F cap W is included in RLP of C, and also that F is included in RLP of C cap W, or that C cap W is orthogonal to F, or that C is included in LLP of F. Sorry, I'm writing the same thing here. No, that's right. C cap W. All right. Or another notation that you can use is also that C is included in F cap W, and that F cap W is included in C perp, right? These are all equivalent notation. You can see all of them in the literature. I guess the one I prefer are these ones, but it's up to you. Okay. So any questions about these lifting properties? So these acronyms are acronyms I'm going to use a lot in these lectures. So I should try to make a note of them, I guess. All right. So let me also note that since C is complete, then meets an initial object that I'm going to denote as the empty set, because this is the initial object in the category of set, and a terminal object. I'm going to denote by a star, so you have to think of it as a singleton, right? Another definition, an object X in C is said to be cofibrant if the unique map from the initial object to X is a cofibration. And fibrant if the unique map from X to the terminal object is a fibration. Right? So these are objects that are special, and these are actually the objects that we are going to say are the models of our model category. They are going to be, for example, projective resolutions or injective resolutions or CW complexes or stuff like that. They are the objects that satisfy good lifting properties that allow to prove some kind of version of the Whitehead theorem, right? So for example, X is cofibrant. This implies that whenever you have something like this, where this is an acyclic fibration, then you can find a lift here. Because implicitly in this diagram, you have the initial object here, but this square always commutes because there is only one map from the initial object to anything. So this is not a condition that this square commutes or that this triangle commute. And so if you have a cofibrant object, then you can always lift any map into the target of an acyclic fibration. And similarly, if A, oh, well, I changed my, if X is fibrant, then whenever you have a map into X and you have an acyclic cofibration into something, then you can extend your map to X. Because implicitly in this diagram, you always have a map to the terminal object. The square always commutes because there is only one map to the terminal object. This is a fibration and this is an acyclic cofibration. So using axiom MC4, you can find a lift here. So these are important things to note, right? And we are going to see in the lectures that these objects, the cofibrant and fibrant ones, are very important. Okay? And just like in standard categories, like for example, chain complexes or topological spaces, you can always replace an object by a better one, like a CW complex or a projective complex. In this category, you can always replace an object by a cofibrant or a fibrant object using axiom MC5, right? You just have to factor the map to from the initial object or to the terminal object. So any object and meets a functorial cofibrant replacement and a fibrant replacement. Oh, sorry. So let me explain. A cofibrant replacement is any object which is weakly equivalent to X. So this is this here, and that is cofibrant. It's a cofibrant object that you can use to replace X because it is weakly equivalent to X. Similarly, a fibrant replacement is some object which is fibrant and which is a replacement of X in the sense that it's weakly equivalent to X. So from the point of view of homotopy theory, they are the same. But from the point of view of doing actual computations with them, they are better, right? So this is the notation I'm always going to use. Q for cofibrant replacement and R for fibrant replacement. And so to answer the question that was asked before, yes, these resolutions are always functorial, meaning that if you have a map from X to Y, then you have a map from QX to QY, which even makes some diagram commutes. Like if you have some map from X to Y, it induces a map from QX to QY, and there is even a map QF between the two that makes the whole thing commute, right? This is what I mean by functorial replacement. Okay? So the proof, you apply MC5 to the unique map from the initial to the terminal object. Okay? So any questions until now? Okay, so before I give examples of model categories, well, I have to give one proposition because it will simplify some things. So I'm going to write some properties and prove them. And afterwards, I'm going to give some examples of model categories. All right? But to give at least one of the examples, I need one of the properties. So another proposition, and this was a proposition if you want. So let C, W, C, F be a model category. So we have a few properties. So I is a cofibration if and only if I is in the left, has the left lifting property with respect to acyclic fibration, which I can also denote like this. Similarly, I is an acyclic cofibration if and only if it has the left lifting property with respect to fibration. P is a fibration if and only if it has the right lifting property with respect to acyclic cofibration. P is, so this is very repetitive, I know, if and only if it has the right lifting property with respect to acyclic cofibration. And finally, F is in W if and only if it can be factored as P circle I, where P is an acyclic fibration and I is an acyclic cofibration. Okay? So what's the point of this proposition? So let's look, for example, at the first one. For the first one, there is one direction which is obvious. It's to prove that if I is a cofibration, then it has the left lifting property with respect to acyclic fibrations, because this is precisely the content of MC4, right? This is what I wrote here. C is included in this thing here. The proposition states that the converse is true. If you have something which has the left lifting property, then it is a cofibration. And this is very important because it tells you that you can express the set, not the set, the class of cofibrations only using fibrations and weak equivalences. All right? If you give these two, then the third one is necessarily fixed. And similarly for all of these, right? And also this one, it tells you that you can express W using acyclic fibration and acyclic cofibration. So let me just first write the proof and then I will write the corollary that I just said out loud. So let's call them 1, 2, 3, 4, 5. So 1, 2, 3, 4 are all similar. So let's only do the first one. And 2 and 3 and 4, you can do them as exercises, but honestly, it's very easy. So to say that I is in C implies that I is in the set of maps which have the left lifting property with W intersect F is part of MC4, right? Whenever you have a cofibration and an acyclic fibration, you can always find a lift. This is part of the axioms of a model category. So now let us prove the converse. And this is an argument which is extremely useful in a lot of cases. So let I from A to B be a map which has the left lifting property with respect to acyclic fibrations. And let us prove that I is a cofibration. And to prove that it's a cofibration, we are going to prove that it is a retract of the cofibration. All right, and then we can just apply axiom MC2. All right, so by MC5, I can be factored as a cofibration followed by an acyclic fibration, like this. So using the left lifting property, we can find a lift H, like this. So you start from A, you go into X, then you go into B. Here, just go into X again, and then you go into B. All right. So this is obviously a commutative diagram. And this is a cofibration. This is an acyclic fibration. So you can find a lift here, a lift that I'm going to call H for some reason. Right. Then this proves that I is a retract of the cofibration. Because you can write a square like this. You start from A, and on the top, you don't change anything. You always have the identity. Then you go to B, and you want to prove that this is a retract of a cofibration. So this cofibration. So you put it here. And how to make this diagram commute? Well, you can go to X using H, and then go back to B using maybe this map P, right? And this diagram commutes. This is a cofibration, because...
Excusez-moi.
Oui.
H, c'est plutôt défini de X dans X, et ça n'a pas grand intérêt, parce qu'on peut prendre H égale 1.
Qu'est-ce que j'ai fait?
À mon avis, vous n'avez pas dû écrire le bon diagramme, parce que ça, H, évidemment, il existe, puisque sans aucune hypothèse, en prenant H égale 1. Et ça n'a pas un grand intérêt.
C'est parce qu'il faut prendre l'identité, il faut prendre I allant de A à X, non?
Non, en fait, il faut mettre un B ici. C'est ça le...
Okay.
Non, c'est pas ça.
Oui.
Si, c'était ça.
C'est bien ça, c'était un B, oui, je pense que c'est bien un B.
Et en prenant la flèche I,
voilà, c'est très bien.
Et c'est l'identité de B à B qui descend.
Ouais, bah oui, en fait,
je pense juste qu'il n'est pas dans le même sens que d'habitude.
Ouais, il faudrait prendre le symétrique pour avoir la même forme que d'habitude.
Oui. Oui, oui. Bon. Oui, là, ça doit être bon. Oui, voilà. Ah non, attendez, j'ai écrit n'importe quoi. Voilà, c'était bon au début. On va le mettre dans le bon sens. Voilà, ici c'est I. Et ici c'est l'identité de P. Voilà, on va le mettre dans le bon sens. Et ici c'est P. Ok, so let me start again. Sorry, there was a slight.
Oui, mais on sait,
Okay,
on sait pas encore que I est dans les cofibrations, donc on ne peut pas enlever.
Non, mais l'hypothèse, so the hypothesis is that I has the left leading property with respect to acyclic fibration. All right, so we don't need to use MC4 here. We use the hypothesis that I has the left leading property with respect to acyclic fibrations. So this is I. This is an acyclic fibration. So using the hypothesis of the left leading property, we can find a lift here without using the fact that it's a cofibration. All right, sorry, there was a slight hiccup. So, okay for everyone? And then you have this H, and P circle H is this thing here, this map, and this map is the identity of B. So this, sorry. So this thing is the identity of B. Okay, and the diagram commutes, you can check. Here you go from A to X using the cofibration here. And here you do I followed by H, and this is precisely I followed by H. This is the cofibration. And here you do, just to go from A to B, you do I. And here you do the cofibration followed by P. And this is, by definition, a factorization of I. Okay? So is everyone, is it okay for everyone, this proof now? Right? Okay, perfect. So this is really a typical example of a proof in a model category. You use lifts all the time, and you try to prove something. Okay. So this is the proof of the first one, and it proves that something is a cofibration if and only if it has the left leading property with respect to acyclic fibration. 2, 3, and 4 are identical. I'm not going to do them separately. Yeah, you can think about it as being part of the fact that C-op is a model category. Yeah, you can do it by duality if you want. So these two are the duals of these ones. So if you know that the opposite of a model category is a model category, then this is okay. But the fifth one, we have to work a little. So for the 5, so 5 is the following. Let me write it again. F is in W is equivalent to F this P circle I, where P is an acyclic vibration and I is an acyclic cofibration. So the implication like this is simply 2 out of 3. All right? If you have P, which is an acyclic vibration, in particular, it is a weak equivalence. If I is an acyclic cofibration, it is a weak equivalence. And by 2 out of 3, the composite of a weak equivalence, of 2 weak equivalences, is a weak equivalence. All right? Now the reverse. If F is in W, factor it by MC5 as doesn't matter, for example, something like this. So this is F, and you factor it as a cofibration followed by an acyclic vibration. But by 2 out of 3, okay, let's say this is I and this is P. By 2 out of 3, I is acyclic. All right, because you have a triangle. Maybe I can write it as an actual triangle, right? You have F, which is acyclic. You have I, which is a cofibration, and then you have P, which is an acyclic vibration. 2 edges are weak equivalences. Therefore, the first one is a weak equivalence. Okay? So again, typical proof using model categories. So let me write down a corollary, and then I will give examples of model categories, and then we have a little break, right? So the corollary is precisely what I said. So the first part is what I said earlier, is that 2 out of the 3 classes C, F, and W characterize the third one. All right? What do I mean by this? I mean that if you know 2 classes out of these 3, then you know the third one. The proof, if we know if we know C and W, then we know F, because this is the set of maps which have a right lifting property with respect to C cap W. If we know F and W, then C is similarly defined as the set of maps which have the the left lifting property with respect to F cap W. And finally, if we know C and F, then we know C intersect W is the set of maps which have a left lifting property with respect to F. F intersect W is the set of maps which have a right lifting property with respect to C, that we know. And therefore, W is the set of maps which can be written as the composition of an acyclic vibration followed, the other way around, an acyclic cofibration followed by an acyclic vibration. All right? So if you know 2 out of these 3, then the third one is automatically forced. Okay? So as a warning, maybe I can just say it orally, because if you give 2 classes, then you can define a third one, which could be the class of cofibration. So for example, if I give you fibrations and weak equivalences, you can say, okay, I define cofibrations as the set of maps which have a left lifting property. This is valid, but this is not necessarily a model category, because you still have to check all the other axioms. You still have to check Well, for example, you have to check that fibrations are the set of maps which have the right lifting property with respect to C cap W, which is not automatic, right? If I give you these two classes and I define C like this, it is not necessarily the case that F is given like this, right? This is a very particular situation. All right, so another corollary that was asked before, W, C, and F are closed under composition. Okay. So the proof. So for W, it's MC2. C and F. So MC2 is 2 out of 3. Right? I said this earlier. For C and F, so let's do, for example, C. So let I and J be two cofibration. Let's prove. That J circle I is in C. And to prove that it is a cofibration, we just have to prove that it has the left lifting property with respect to acyclic fibrations. Okay? So we take a diagram like this. Maybe not B here, X. So you take an acyclic fibration and you want to check whether there exists a lift like this. Okay? And if you can do this all the time, then it proves that this map here is a cofibration because it can be lifted against any acyclic fibration. All right? But now what you can do is to rewrite this diagram. So let me keep this one. You can first rewrite the diagram like this. And find the first lift here. Because this is a cofibration, this is an acyclic fibration. And now you have a new diagram like this. This is J, this is I. And you can find a map like this. Again, using MC5. And now if you combine the two, you get a map from C to E, which is precisely the map you wanted here. And you can check that this commutes. Right? This commutes. This one is this one. This one is this one. And this one is this one. All right? So you can lift the first one, then the second one, and you get a lift of the total field. All right? So you don't need to assume it in the axioms of a model category. It actually follows from the properties of the model category. Okay? Well, let me just finish this corollary, then we can have a break. I know it's already 4:45. So C and C cap W are closed under pushouts. F and F cap W are closed under pullbacks. So what do I mean by this? I mean that, for example, this one, if you have a cofibration here, and you take a push out, then the corollary says that this map is a cofibration. And if it's acyclic, then this one is acyclic too. Okay? And similarly, if you have pullback like this, then the corollary said that this map is a fibration, and if this one is acyclic, then this one is acyclic. Okay? And you have to be somewhat careful about this proposition, or this corollary, because it is true about cofibration, it is true about acyclic cofibration, but it is not necessarily true about weak equivalences. That the push out of a weak equivalence is a weak equivalence. Okay? This is only true for acyclic cofibrations. And similarly here, if you want to prove that the pullback of weak equivalence is a weak equivalence, you have to check that this one is a vibration. Otherwise, it's not necessarily true. Wait.
Sorry.
Yes?
The diagram of the push out is in the bottom, it's not A union X, it's B union X.
Oh, right. Yeah, sorry. So let's go about the proof. So for the proof, we are again going to use the fact that all these classes are defined by lifting properties, right? So for example, let us prove that cofibrations are closed under pushouts, and you can do the other three checks. So for example, let's say that you have a pushout. Sorry, I don't know if you hear this noise. There is work in my building. So let's assume that you have a cofibration here, and you want to check that this one is a cofibration. All right? Well, all you have to do is check that you can lift it against any acyclic fibration, right? This is what we proved in the proposition. But now what we have is if you look at the outer diagram, we have a cofibration and an acyclic fibration. So we can find a lift like this that makes everything commute. And now I can write it in a more usual way. You have A goes to X, goes to B, goes to the push out. And you have E here. Here you have this map. And here you have this lift. And by the universal property of push out, there exists a unique map which makes everything commute, which maybe I can draw in red. And this map in red is the lift that you wanted. All right? So is this okay for everyone? Okay, one last corollary, and then we can have a little break, and we can ask questions or go have a break. Isomorphisms are in C, W, and F. And the proof is that, well, isomorphisms lift against anything. All right. If you have, for example, a diagram like this, let's see where, like if you have a diagram like this, if this is an isomorphism, you can always find a lift, whatever this is, whether it's a fibration or a cyclic fibration or anything, we can just use the inverse map. So for example, if this one is an iso, let's see, this is pi and this is p. To define the lift, L, you can just take f circle phi minus 1. And this is the lift. All right?
Excuse me.
Wait.
In the last proof, why is the bottom triangle commutative?
Which one? This one?
Yes.
So this one is, so when you go from B union A to X to Z, so you have to look at it like this. So when you go from B to E to Z, so you go like this. This is the same as going like this. All right. And this is the same as this, which is the same as this. So basically this map. And you want to, sorry. So you want to check that this composition is equal to the direct map from B union AX to Z. Let me think. So let's see. This is F. This is P. This is L. This is L prime. So we want to check that P circle L is equal to F, but P circle L so you want to compute this composite and you want to check that it's equal to F. Oh, yeah, okay, sorry. So to check that it's equal to F, you have to prove, to use the fact that there is a unique map from the push out to Z, such that the composite from X to Z is equal to some map, and the composite from B to Z is equal to some other map, right? So you have to check that the map, which so let's say the square is like this. You have to check that there is the map like this is equal to the map like this, and that the map like this is equal to the map like this, right? Because by the universal property of the push out, there is a unique map from the push out to Z, such that the composition with this map is equal to this map, and the composition with this map is equal to this map. All right. So you have to use the universal property of a push out. Okay. It's a small exercise. All right. So in the last diagram of the last corollary, YPL equals G. Well, this is exactly what I. Oh, is the question on the chat the same as the question that was asked out loud? In this part here. Oh, because well, PL is equal to PF phi minus 1, and PF is equal to G phi because the square commutes. And so this is equal to G. Right. Any other questions before we have a small break? No? Okay, so we can have like a 5 minutes break and we meet again at 5. All right, so we can start again. So as promised, I'm now going to give some examples of model categories, because what's the point of making a definition if we don't have anything to work with? So let me start with, as is usual in mathematics, with trivial examples. So we have 3 trivial examples. So let C be an arbitrary category. one can check that the following define model structures on C. All right, so maybe I said it at some point, but model structure is a way of saying three classes of morphisms which satisfy the axioms of a model category, right? So the first one, WCF, you take all isomorphisms for W, and then fibrations and cofibrations are anything. The next one, you take, for weak equivalences, you take everything. So the things that you want to invert are all the morphisms. So the localization will be completely trivial. For cofibration, you take isos. And for fibrations, you take anything. And you have the dual one, where you take cofibrations are anything and fibrations are isomorphisms. All right. This is a little exercise. You can check that these define model category structures. Of course, they are completely pointless. But their only merit is to exist, basically. But still, at least you have examples. Why do I say they are pointless? It's because what's the point of a model category? As I explained last time, the point is to invert weak equivalences. Here you only invert isomorphisms, which are invertible anyway. So what's the point? And here you invert everything. So if you invert everything, then it means that your category becomes trivial, becomes equivalent to a trivial category, either empty or just a point. Oh, okay, so maybe I should say it should not be arbitrary, the category, it should be complete and co-complete, because otherwise MC1 is not satisfied. Another example, if C and D are model categories, then so is C cross D, right? You take the product of weak equivalences, the product of cofibrations, and the product of fibrations. All right, this is again a small exercise. Check that this works. Okay, it's not very hard to check. And finally, if C is a model category, then C up is a model category with, so for weak equivalences, you take the same ones. Of course, they are reversed. For cofibrations, you take fibrations, but reversed. And for fibrations, you take cofibrations, but reversed. Right? You have to invert fibrations and cofibrations. Because if you look at, for example, a diagram like this, in the opposite category, it becomes something like this, right? And left and right are exchanged. But cofibrations are always on the left and fibrations are always on the right. So you have to invert things. Okay. Let me also make a small remark. As you see here, I'm making a slight abuse of notation, like I write WC up as if it made sense to talk about the weak equivalences of C up, right? This is additional data that you put on your category. for a given category, there can exist many possible WC op. For example, here, for any category, you already have 3 examples. Okay? And you can even have examples where the weak equivalences, so the most important things, are the same, right? And where the auxiliary data, the fibrations and cofibrations are different. Okay, so this is something to think about. Okay, so any questions about these examples? They exist. That's pretty much all there is to say about it. This one is interesting because a lot of propositions and so on can be proved using dual arguments. For example, like your comrade noticed earlier, point 3 and 4, if you prove point 1 and 2, point 3 and 4 can be proved by saying, okay, we have proven it for any model category. We apply it to C up, and we have 3 and 4, right? So this is often going to be the case. Right, but for many applications, it's important to have both statements, one about cofibrations and one about fibrations. But typically, they are proved in the same way. All right, so now let's move on to more interesting examples, I guess. So the first one is due to Quillen, and it was pretty much the first example of model categories. So the category of topological spaces, well, I have to be honest, I am lying a little bit. You don't have to, should not take all topological spaces. You should take something like weakly Hausdorff compactly generated spaces, something which has good categorical properties. But this is really something very technical, but is not something I want to dwell too much about. If you want to learn more about this, you can read online about convenient categories of topological spaces. For now, I will be a little bit of a liar and say I'm working with topological spaces, but anyway. So this category has a model structure where W, so weak equivalences are weak homotopy equivalences. And of course, I write example here. It should be more of a theorem, right? Fibrations are Serre fibrations. Okay. And if I wanted, I could stop here, right? Because I have given you W and F, I do not have to give you C, right? Because C can be defined as morphisms, so continuous maps, which have the left lifting property with respect to acyclic fibrations. So Serre fibrations, which are weak equivalences. Of course, this is not satisfying at all, right? We want to actually be able to work with our category, and we want to know what cofibrations are. But from a theoretical point of view, I could just say C is continuous maps which have left lifting property with respect to acyclic fibrations. Actually, it turns out that in this case, there is a nice description of cofibrations. So these are retracts of generalized relative CW complexes. Right. Someone asks if it works with UIVX fibrations. Yeah, precisely. It's another example which I'm going to give right now. So, but the first example was really for this model category, where you want to invert weak homotopy equivalences, but this was basically a motivation for model categories. What you really want are homotopy equivalences, and to invert homotopy equivalences, you have to deal with models, and models are, as we said earlier, or on day, generalized CW complexes. Well, and so when you have a model category like this, as I said, what you really want are models. And so it's typical to describe fibrant and cofibrant objects. So here, all objects are fibrant, and cofibrant spaces are, well, retracts of generalized CW complexes. Right? So the models, in the sense of model category theory, will be things which are at the same time fibrant and cofibrant. So of course, here fibrant is not a condition, but cofibrant are retracts of generalized CW complexes. These are the spaces that satisfy the Whitehead theorem. Okay, so there is a question, what are the maps? The map coming from the pair of the relative CW complex. So in the category, the maps are just continuous map. Here, relative CW complex means that you start. So cofibration is something which has the form A, is included in A union X0 union X1 union blah blah blah, where X0, X1, and so on are obtained by gluing cells to a previous thing, right? So this is a cofibration. But the maps are just continuous maps. Okay? Does this answer the question? With the chat, it's not.
I didn't understand what were the cofibration, but I think this is.
The questions are what are cofibrations? So cofibrations are generalized relative CW complexes. So what is a relative CW complex? It's something where you start from an arbitrary space, then you glue cells, then you glue cells to this, then you glue cells again, and you do it as many times as you want. And the inclusion is what is called a relative CW complex. Or if you don't glue cells in the order of dimension, is what is called a generalized relative CW complex, right? And as I said, you have to deal with retracts because if something is a cofibration, then so are its retracts. So there is another question. Is there a VAT missing? Where would you put that? So all objects are fibrant, right? This is a sentence. And cofibrant spaces are retracts of generalized CW complexes. Okay, is it okay? Okay. No, it's okay. By the way, someone asked last time, what's the difference between a generalized CW complex and a CW complex? So there are spaces which are generalized CW complexes, which are not homeomorphic to CW complexes, right? I gave the example on Slack, but I can, and now it's in the notes. It's example 1.3.13, I think, something like this. Basically, you start with an infinite number of vertices. You glue an edge like this, all right? And then, and this is what is forbidden in CW complexes, you glue edges. Maybe I should put it in this direction. You glue edges after you have already glued in edges. which is forbidden in CW complex. So you glue one like this at 1, then at 1/2, then at 1/3, and then 1/4, and so on. And so you can prove that this space is, by definition, a relative generalized CW complex, is not a CW complex. It's not homomorphic to a CW complex. Because you can read the example in my notes, but basically the idea is that if it were a CW complex, then it would have dimension 1, because hk of x relative to, so the relative homology like this is 0 for all k greater than 2 and for all x. All right, so it has to have dimension 1. Now, if you have something of dimension 1, and you look at these vertices here, well, these points have to be 0 cells if it were a CW complex, because if you look at h0 of x relative to this point, it is isomorphic to Z3, right? And in a graph, in a CW complex of dimension 1, if it's something in the interior like this, the rank is 2. Okay, so here it's 3, so it has to be a cell. And now you have a sequence of cells, of 0 cells, so vertices, which converge to this cell. And this is not possible in a CW complex because the space, so the 0 skeleton, is discrete. And so you cannot have an infinite sequence which converges to something. It has to be constant after some time. So it cannot be a CW complex. Of course, it's homotopy equivalent to a CW complex. You can just make a homotopy which puts everything to the side here, and this becomes a wedge of segments, right? But it's not homomorphic to a CW complex. All right. You can read the notes and have a look at it. Anyway, let's go back to the examples. So the first example of Quillen was the category of topological spaces where you have weak homotopy equivalences, self-vibrations, and retracts of generalized CW complexes. So this was really the first example of model categories. There is another, so maybe I can make dates also. So this is 67. So some years later, you had Strum. So this is a O with a slash in it, right? So Strum in 72 found a model structure where you have another structure. So W are strong homotopy equivalences. So this is some kind of a weird example because here the weak homotopy equivalence already satisfy Whitehead theorem, which is to say that they have a homotopy inverse. So, but anyway, you take cofibrations are retracts of Hurwitz cofibrations with closed image, so a bit technical conditions, and fibrations are Hurwitz fibrations. Right? So this is another example of a completely different model category. Right? These two are not, if I remember correctly, they are not equivalent in the sense of model category, something that we are going to see later. And here, any object, any space is fibrant and cofibrant. It means that any space is a model, right? Yeah, I guess it's also compactly generated weakly Hausdorff spaces. Okay, so this is really a completely different example. You should not really think that these two are similar at all. This one is a bit strange, as I said, because, well, any space is a model, so any space satisfies the Whitehead theorem because any strong homotopy equivalence is by definition something with a homotopy inverse. Anyway, there is something which is a mix of the two, so which is due to Cole in 06. Top, again, completely generated with Leostorff, has a mixed model structure where you take for weak equivalences the weak equivalences of Quillen, and for fibrations you take the fibration of Strom. So you combine the two like this and you get, it is a theorem, it is not obvious that this is a model structure. So you can check, let's see, which is again the set of maps which have a left listing property with respect to acyclic fibrations. But this is the set of I, which is a cofibration of Strom. So you have X cofibration with a closed image such that I is equal to F circle J. F is a strong homotopy equivalence, and J is a Quillen cofibration. So this one, is it equivalent to the one of Quillen? I would say yes, because they have the same weak equivalences, but I would need to check. I'm not completely sure anymore. I would need to check. There is a good reference for this, is the book of May and Ponto, which I think I give in my bibliography. All right, so as you can see, one category can have many different model structures, right? And the choice of model structure really depends on what you want to do with it, right? It's not, like, there is not one which is better than the others. It's really dependent on what your applications are. All right, so there is a question, what is an equivalence of model categories? It's a bit complicated. We are going to study it, yeah, in section 5, I guess. Right, so even section 6, yeah, section 6. So not in at least 2 weeks, right? All right, let me give other examples. You have a category of simplicial sets. So this one is also due to Quillen, I think. So simplicial sets as a model structure. So weak equivalences are, well, you can guess, weak homotopy equivalences. Cofibrations are just injections. And fibrations are can fibrations. And we are going to see in chapter 2 that this model category is equivalent to this one, in a sense that we are going to define later on, which is a sense that will basically say these two categories have how to say equivalent homotopy categories, right? No, it's the category of all simplicial sets, and fibrations are can fibrations. And so all objects are cofibrants, and fibrant objects are can complexes. So I guess you are asking this question because of what was said at the end of the lecture of Homotopy 1, right? It's because, yes, in the homotopy category, you will only see models, that is, fibrant and cofibrant objects. And the models are, in this case, can complexes. But the category itself contains all simplicial sets. All right. So let me give the last examples. The category CH of R has several model structures. So if you recall CH of R, were Z graded chain complexes, right? So the projective, so it's a name, right? The projective structure where W are quasi-isomorphisms and vibrations are surjections. The injective structure where similarly W are quasi-isos, but cofibrations are injections. Okay, and here I'm using this property of before. I have given you two classes. The third one is fixed. You don't have a choice, right? C is simply W cap F, and F is C cap W. And in this case, it is not easy to describe these classes, right? There is no good description. So for example, in this case, cofibrations are in particular degree-wise split injections. So by this, I mean that it's a map of chain complexes which is an injection, and such that for each degree, this injection is split, right? There exists a retract. But the converse is true, is false. Right? If you have a map which is a degree-wise split injection, it's not necessarily a cofibration. Actually, it's very difficult to describe cofibrations. There is no, as far as I know, there is no good description of cofibrations, except maybe if you are over a field or something, but in general, it's very difficult. Right. Christian. Does the situation improve with our field? Yeah, it's a bit simpler, but it's still difficult when you are with Z-graded chain complexes. There is a third one, which is Strom structure. So it's not actually due to Strom, but it looks like the Strom model structure. So W are homotopy equivalences. So things which already have a homotopy inverse. C is a set of maps which have the left lifting property with respect to all maps like this. So B is any chain complex, and I is cellular chain complex of the standard simplex. So basically, B star I star is Bn plus degree n plus Bn plus Bn plus 1 with an appropriate differential. So it's a bit complicated. I'm not going to spend so much time about it, but you can think of this as some kind of like, if you remember the definition of Hurwitz cofibration, this is very similar, right? This is maps which have a left-lifting property with respect to something like this, right? Where I is 0, 1. So this is extremely similar. And fibrations are maps which have a right-lifting property with respect to this one. Okay? Well, this one is a bit more complicated. I don't want to deal too much time with it. All right. So as you can see, again, one category, many model structures. It really depends what you want to do. Even if you have the same class of quasi-isomorphisms, of weak equivalences, you may have different auxiliary data, so cofibrations and fibrations. It really depends what you are interested in. If you are in a setting where you are more likely to deal with projective resolutions, then you are going to deal with this model structure. If you are in a setting where you are going to deal with injective resolutions, then you are going to use the second one, and so on. It's really dependent on what you want to do. Let me mention that CH greater than 0 has projective structure. So you take the same, you take quasi-isomorphisms and surjections, in which then, in this case, you can describe cofibrations. There are injections with projective, hence the name, cochains. Injections, in degree greater than 1. And CH lower than 0 has an injective structure. So injective means you have quasi-isos and injections, and fibrations are surjections in degree less than -1 with injective kernel. So injective in the sense of an injective resolution, right? So when you bound the degree, so if the degree is bounded below, then you can deal with projective resolutions. And here your models will be projective complexes, right? And you have some kind of Whitehead theorem. Similarly here, if you are bounded above in degree, then you can have an injective structure in which models are injective resolutions. Right? So are there any questions so far about these examples? So as I said, here I just listed examples and told you there are model categories. It is very hard to check. Well, very hard. It's not. I mean, it's not trivial to check that they are model structures. There is a question in the chat. What are the weak equivalences? In the last two examples, they are quasi-isos, right? So here, sorry. So here, W is quasi-iso, and fibrations are surjections. Here, W is quasi-iso, cofibration is injections, right? So one of the goals of this chapter is to prove this one, right? We are going to prove that this is a model category. which is already not easy. The first two are these two Quillen equivalent? If I remember correctly, yes. And yes, that's why we can deal either with injective or projective resolutions, right? You know, for example, if you want to compute the X functor, you can either take a projective resolution of the source or an injective resolution of the target. Yeah, it's not necessarily that they are Quillen equivalent. It's more like they have the same class of weak equivalences. And so when you want to compute derived functors, you have to check, you have to add some additional data so that you have a model structure, and then you can do this whole business of Quillen functors and derived functors of Quillen functors. So you can fit all you know about homological algebra in one of these two settings, basically. And they are not so different because they fit in this same setting. Right? But are they Quillen equivalent? I have to check. So there is a question, do we have results on links between different model structures on a category? I mean classification, invariance. To my knowledge, there is work about this, but this is more like, I would say, a current area of research. If you are interested, last year, homework, you can look on my webpage. The homework was to check, prove, more precisely, that there are exactly 5 model structures on the category of pointed sets, which, I mean, I guess it's the first time you say the definition of model categories, but this is a really surprising result, because to be able to think that you can count the model structures on the category is it's a bit outlandish, but it's true. In this case, at least. Right, so you can try to do the homework. There are still some things at the end. So there is the subject on my webpage. There's also the solution, but I guess if you want to do the homework, you should not look at the solution first. There are still some questions at the end where we have to use some notions that we haven't seen yet. You will be able to do the homework in maybe a week and a half, I guess. But yeah, and it's a really surprising result. But in general, to count the model structure is it's a bit of a strange notion. To classify them, you can classify them according to what we are going to learn about just now, which is the localization. And then you have Quillen equivalences between model structures. So we can say whether two model structures are equivalent in a nice sense. But invariance and so on is not, I would guess that there are some people working on that, but it's not something I'm aware of. Probably it exists. All right, so any questions about all this before we briefly start the next part of the chapter? No? All right, so what we are going to study, well, in the last 5 minutes and in much more detail Monday, is the homotopy category, which is really one of the goals of model categories, is to study this homotopy category. So what is the homotopy category? Is something that you saw last semester. It's the localization of a category with respect to the class of weak equivalences. And for this, to define this, you don't need cofibrations or fibration. You just need some class of morphisms. So let C, should not write C like this. So let C be a category, and W class of morphisms. The localization of C with respect to W is a category C bracket W minus 1 equipped with a functor lambda, so lambda L is in localization, of course, from C to C bracket W minus 1. Okay, so someone asked me before, I think you have to add it in the definition, sending such that two conditions. For an F in W, lambda of F is an iso. And the second condition, for any functor from C to D such that F of F is an iso, there exists a functor from, I should write always C like this to not confuse it with cofibrations. So there exists a functor from the localization to D such that the following diagram commutes. There exists even a unique functor up to equivalence. So this is my notation for unique up to equivalence. And this diagram commutes up to natural equivalence. Oh, no, it commutes strictly, maybe. Yeah, let's say it commutes strictly, but functor is only defined up to equivalence. So equivalence means here natural isomorphisms. Right? So as a remark, note that lambda sends F W to isos, but not all morphisms sent to isos are in W. Like you could have a weird possibility of a localization in which you have more maps which are sent to isos. For example, you can think about some example where, for example, you take Z and you localize at 0, right? Well, everything is sent to, like, if you take the ring, like if you know the localization of a ring, if you take the ring Z and you localize, you invert the element 0, then everything becomes 0, and then everything is basically a unit in the target ring. And so to conclude today, let me just state that the localization exists and is unique up to natural equivalence. So you proved this in the course Homotopy 1. And so to finish, let me say that working in the localization is very hard in general. For example, determining if two morphisms are equal is hard. The goal is to use the structure of a model category, C, W, C, F, to make computations in C bracket W minus 1 easier, more concrete. So this is the goal for Monday. What we are going to do Monday is we are going to start with a model category. So when you have a model category, you have this class W, and you can consider the localization. And this localization only depends on W. But to work with it, to actually make computations, we are going to use this auxiliary data, cofibrations and fibrations. Right? So I guess that's time to stop. So are there any questions before we end the recording? No? Right, so I will stop recording.